I'm recording this. So if you're watching this as a video, pause, try the warm up, and then come back. All right. Again, this is going over the previous lesson, the day 3 notes on solving log equations. Okay, this is what we were practicing in the ALEKS part 2 or practice 2 assignment. So you want to isolate the log expression, the log term. So we need to get that 4 and that -2 to the other side. Okay, when you're solving, you always want to move your constant first. So we're going to add 2 because that's the opposite operation. And what you do to one side, you do to the other. So you end up with 4 log base 2 of x equals 16. Then you need to get rid of your coefficient. So we're going to divide out that 4. That's the opposite operation. And we end up with log base 2 of x equals 4. Now, when you're trying to solve a log equation, we talked about several different methods in our notes. We said you can exponentiate both sides. You can rewrite from log form to exponential form, or you could do the graphing. Now, if you were going to do the graphing, you wouldn't have even had to have bothered with these steps. You could have just entered the left side as function 1 and the right side as function 2 and looked for the point where they intersect. Okay, but when we're solving algebraically, either by exponentiating or changing to exponential form. Do y'all have a preference on those methods? Which method? If nobody cares, I'm just going to rewrite it in exponential form. That's my preferred method. So remember, and you can write this at the top of your notes again or over here as reference. Okay, what you need to remember, it's in our other notes, but we'll put it on these as well. When you have your log, okay, let's say it's this format, or you don't have to use Y, you can use A, it doesn't matter what these letters are. Okay, you want to rewrite that into exponential form, and I'm putting an arrow on both sides here because this goes from log to exponential, but you can also go from exponential to log. The base becomes the base of the exponential. What the log was equal to is the exponent, and the argument of the log is what the exponential is equal to. So when you're converting back and forth between forms, you need to remember that conversion, I guess, is what you could call it. All right, so our base is 2. So I'm going to rewrite this as a 2. And then my exponent would be the 4. And it would be equal to x. So now I've solved for x. I've isolated the x. I just need to simplify. What is this actually equal? What is 2 to the 4th power? 2 times 2 times 2 times 2. 16. Thank you. Okay, if you chose to try this by graphing, you should have gotten the same thing. Or if you chose, once we isolated the log expression or log term, if you did exponentiating both sides, you still should have gotten the same thing. All right, so let's discuss the inverse relationships. Just inverse relationships in general. This is not new information. We have talked about this with every set of inverse functions we've worked with. Okay, most recently that was cube and cube root functions. Before that, we talked about quadratic and square root functions. They have the inverse relationship. And now we're dealing with exponential and log functions, their inverse relationship. But in all inverse relations, your x and y values or inputs and outputs switch. Okay, you interchange your x and your y. Okay, a relation and its inverse relation are always a reflection graphically across the line y equals x. If you need a reminder of what the line y equals x is, remember it's the linear parent function. It's got a slope of 1 through the origin. That's the line y equals x. And that's the line that your function and its inverse will reflect across. Okay, we write the inverse using the -1 as the little power there as a superscript. Remember, that's how we indicate that it's inverse. Okay, and the way that you read that is f inverse of x. This is the same process we've talked about multiple times before. To find the inverse algebraically, you replace f of x with y if you need to, if necessary. If it's already written with a y, then obviously you don't need this step. You switch the x and y. Now, oftentimes I combine these two steps into one, and you'll see what I'm talking about when we get to the examples on the back. Okay, then you isolate the term, either the exponential or the log term, whichever form it's in. You isolate that, so you get other things moved away from it to the other side. Then you will rewrite it. If it's starting as a log, you'll rewrite it as an exponential. If it's starting as an exponential, you'll rewrite it as a log, because you're trying to solve for y. Okay, so that last step is doing this, going from exponential to log or vice versa. Okay, so you've got to know what goes where when you're rewriting it. So we're going to try those steps in these two examples, and we're going to look at what those graphs look like. And then we'll flip over to the back and we'll just do the algebraic practice. We won't worry about graphing. Okay, so step by step, if I have this function, my first step is to replace f of x with y so that I can then switch x and y. Now, I want to solve for y. So y is in the exponent of this exponential. I'm going to need to rewrite it as a log so that I can solve for y. So the base is 2. So this becomes a log base 2. Okay, and then what the exponential was equal to becomes the argument of the log. And what was the exponent is what the log is equal to. Now I'm going to indicate that this is the inverse function with that little -1. But they want us to put it back in function notation, meaning f of x instead of y. So I'm going to replace the inverse of y with f inverse of x. And then it's the log base 2 of x. So that's your inverse. So I'm going to draw the graph of the original f of x. I'm going to use gray. If you don't have two colors, just do this first one lightly in pencil and then do your other one darker, okay? So this is an exponential parent function. There's no transformation, right? It's not shifted anywhere or stretched or reflected. Okay, so we need to think back to our exponential parent functions. They have a horizontal asymptote along the x-axis. Okay, remember it's y equals 0 is the asymptote. Okay, they have a y-intercept at 1, and that's because if I input a 0, anything to the 0 power is 1. So if I input a 0, I get an output of 1. So 0, 1. Now, if I input a 1, what's 2 to the first power? So if I input a 1, I get an output of 2. So there's a point at 1, 2. If I input a 2, what's 2 squared? So there's a point at 2, 4. If I input a 3, that's 2 cubed is 8. So there's a point at 3, 8. And that's plenty of points. And I'm going to use the asymptote to guide that end behavior and go through these points to sketch this curve. So that is the f of x that we started with. Now, I'll do the inverse. I'll do this one in blue. So this is a log parent function, right? There's no shift or stretch or compression or reflection, just log base 2 of x. So I need to remember, okay, that means there's a vertical asymptote at x equals 0. So my vertical asymptote then remember, we talked about if you take the log of 1, it doesn't matter the base. Log of 1 is 0. It can be log base 2, log base 10, natural log, any base. Log of 1 is 0. Okay, so the x-intercept here is at 1, 0. Okay, and if you take the log of something and it matches the base, so log base 2 of 2, that's just a 1. Okay, so if I insert a 2, I get an output of 1. So there's a point at 2, 1. Okay, and you'll notice these x, y points are just switched. So this was at 0, 1, now it's at 1, 0. This was at 1, 2, now it's at 2, 1. You can just invert the x and y of each of these points because that's what the inverse relationship is. So even if you don't know more logs off the top of your head other than those two, you can say, okay, well, this was at 2, 4. So here I'll have one at 4, 2. Okay, this was at 3, 8. So I'll have one at 8, 3. And then I can use those points and the vertical asymptote to guide my curve. That is the inverse function. So that is the function and its inverse. And visually, if it is helpful to you to have that line y equals x, you can put that in there as a dashed or dotted line. Oh, I don't know why that little spot went there. Get rid of that. That's the line y equals x. That's what this is a reflection across. So if I folded it over that line, every point there would match up. The asymptotes would match up, right? So those of you who are more visual, you can look at the graphs of your functions together to see if they're inverses. If they reflect across this line, y equals x, they are inverses. Or you can just click and check points. Click and check on Desmos. If you click there, it'll say that that is 0, 1. And then you should be able to click here and see that that's 1, 0. And you can verify the x and the y are switching. You can just click on points to check. All right, let's try this with B. So now we're starting with a log equation, and it's not just a parent function. There's a transformation here. Just for fun, what is the transformation that's happening here? What does that plus 5 do to the log function? Is that plus 5 inside or outside the function? Outside. So it's your k value. What does k do to your graph? Up or down. So it's plus 5. So that means this is the log function shifted up 5. And this is a common log, a base 10 log. So actually, I'm going to go ahead and graph. I have to graph both anyway. I'm going to go ahead and graph this original function. So I'm going to go ahead and graph this one in gray over here. So our log function shifted up 5. Now that means my vertical asymptote hasn't moved. It's still at 0 because shifting up and down does not move a vertical asymptote. A vertical asymptote goes up and down forever anyway. Okay, but shifting up 5 does move what is normally my x-intercept here, which is normally at 1, is going to be shifted up 5. So instead of having a point at 1, 0, there's a point at 1, 5. All right. Now you could test some other points. This is a base 10, right? If no base is written, it's a base 10. We know, so if we input a 10, log base 10 of 10, that's going to be 1. Plus 5 is 6. If I input a 10, I get an output of 6. So there's going to be a point at 10, 6. So now I've got a couple points and my asymptote, and I can use those to sketch my curve. My curve should not have come back out away from the asymptote like that. I'll try and draw that better. So this is the original function. So now we're going to find the inverse and then graph it. So first I'm going to replace f of x with y. And I'm going to switch x and y. Now I'm going to solve for y. Before I can rewrite this from log to exponential, though, I've got to isolate the log expression. So that plus 5 needs to move by subtraction. So that's going to become x minus 5 equals log of y. Now I'm ready to rewrite that as an exponential. The base is an understood 10. So this is 10. And then the exponent is what the log was set equal to. So that's x minus 5. And then the argument of the log is what the exponential equals. So now I've solved for y by rewriting it in exponential form. Now I'm going to indicate that's the inverse. And then I'm going to rewrite it in function notation. That just means with f of x instead of y. And then I'm going to graph this one in blue again. So this is the exponential function, a base 10. And what does that minus 5 inside the function do? Right 5. Okay, it's inside, so it's left or right. And remember, it's the opposite. So this is the exponential parent function shifted right 5. Now remember, with the exponential, we have a horizontal asymptote. And shifting left and right is not going to move that off of y equals 0. So I'm going to have this horizontal asymptote. Okay, and let's see. If I input a 5, that would make this exponent 0, right? 5 minus 5. What's anything to the 0 power? So there's a point at 5, 1. So 1, 2, 3, 4, 5, 1. Okay, then I could say, okay, what if I input a 6? 6 minus 5 is 1. And what's 10 to the 1 power? 10. So if I input a 6, I get an output of 10. So there's a point at 6, 10. So now I can go through these 2 points and use the asymptote as the guide for the end behavior. So I can see, and really, let me try and draw that again more on the asymptote. There we go. So that's the inverse function. If you need the visual, draw the line y equals x. You can do it as a dashed or dotted line. But that helps make it very clear that this is a reflection across that line, isn't it? If I folded it on that line, wouldn't all the blue and gray points match up? Y'all agree? So you can see sometimes they're on opposite sides of that line. They don't intersect. They can intersect though. They can cross that line and intersect each other and cross that y equals x and still be inverses. And it would look something like this. Okay, in Desmos. Just going to show you what that looks like in Desmos. So that function was log of x plus 5. or minus 5? Plus 5. And then the inverse we said was 10 to the power of x minus 5. Oh, I did do that in blue. And then if you want to write that line, y equals x, you literally just type in y equals x. And you can make it whatever color you want, and you can make it dashed or dotted. So you can see something. Did I do write something wrong there? Doesn't match. Let's see. Oh, my minus 5. I was like, that doesn't look right. My minus 5 didn't go in the exponent. That's why. If you're having trouble, when I do that a lot, I sometimes don't even catch it, but I can see that didn't look right in the graph. Use a parenthesis around your exponent so that what you type up there will stay in the exponent. There we go. So now it matches what we graphed here by hand. So if you don't want to graph it by hand when you're testing, okay, you can just plug it in. Plug in the original, plug in what you got for the inverse, and plug in y equals x. So you can see, does it fold over that line? Would all these points match up? And they do. Okay, so if you need the visual to check for inverses, you can. If you have a multiple choice question, you don't know the inverse, they're asking you for the inverse. You could simply graph the original and then graph answer choice A. See if they look like inverses. If they don't, graph answer choice B with it, and then answer choice C and D, and look at them and see which one is the reflection over that line, y equals x. I feel good about that? All right. So let's just practice the algebra, okay? We're not going to worry about graphing them. We're just going to practice finding inverses, and this is the same process with any function that you want to find the inverse of. Replace f of x with y, switch x and y, solve for y. Now, the solve for y part is a little different for these because to solve for y, you have to convert from log to exponential or exponential to log. Okay, so you do have to remember that transition between the two forms. All right, so like I said on the front, I like to combine step 1 and 2, replacing f of x with y and switching x and y. So I'm going to bring that x over here, and that's going to become the y. Now, to solve for y, I first have to isolate the exponential term. So I need to get rid of that times 2. So I'm going to divide it out because that's the opposite operation. Now I've isolated the exponential term. I'm ready to rewrite this as a log to solve for y. So the base is 10. So this is going to be a common log. I don't have to write a base 10. Just log indicates that it is a base 10 if you don't write another base. Okay, of x over 2 equals y. Now I do need to indicate that's the inverse of y. Okay, now we started in function notation, so technically we want to end in function notation. So we just like to rewrite instead of inverse of y, f inverse of x. And it equals log of x over 2. All right, in B, we start log. We still start the same way though. Replace f of x with y and switch x and y. We need to isolate the log term. So again, isolate the over here. We isolated the exponential term. Here is our log term. We're going to isolate. So we need to get rid of that minus 8 by adding 8. So we have x plus 8 equals 1/3 times the natural log of y plus 2. Now, how do I get rid of that 1/3? Say it again. Multiply by, what's going to make a 1/3 cancel out? A 3. So I'm going to multiply by 3. Some people want to say divide by 1/3 because the 1/3 is being multiplied and the opposite is to divide. Yes, you can divide by 1/3, but multiplying by 3 is the same as dividing by 1/3. Okay, and it's a little more straightforward. So if I multiply by 3, that's going to allow those 3's to reduce. So that's the whole point of this. And what you do to one side, you do to the other. So I have to multiply this side, the entire side. So I put it in parentheses by 3. So that's going to have to distribute. So that is 3x plus 24 equals the natural log of y plus 2. I've isolated my log expression, so now I'm ready to rewrite this as an exponential. What is the understood base when you see ln? What is the base here? E. ln means natural log. When you see ln, your natural log, your base is an understood e. So this is a base e to the power of this whole side over here. So 3x plus 24. And it equals the argument of the log, which is y plus 2. Now I'm not done. I haven't solved for y yet. What do I still need to move? To get y by itself. Yeah, that plus 2 needs to get out of here. So I'm going to subtract 2. Now, when I subtract 2 over here, it is not in the exponent with that 3x plus 24. So I am not doing 24 minus 2. This minus 2 is outside the exponent. I'm going to go ahead and replace the y back to function notation. So this is e to the 3x plus 24 and then minus 2. So make sure that that minus 2 is not in the exponent with the rest of that. So far, so good? Okay, let's try the next one then. All right, so we've got base e to the 2x plus 3. So this one is, we're going to replace f of x with y and then switch the x and y. So that is going to look like this. Oops, I don't know why I wrote a plus there. That is a minus. Now we need to isolate the exponential. That is not what I meant to highlight. Come on. This is the expression that we're isolating. So we need to get rid of that plus 3 by subtracting 3. So now I've isolated the exponential and I'm ready to rewrite this as a log. Now, if this is a base e, what type of log am I going to write this as? What was it over here? How did we end up with a base e? What kind of log did we come from? ln, natural log. So when I rewrite this from exponential to log, it's going to be a natural log because it's a base e. So it's going to be the natural log, and I don't have to write the e, it's understood, of x minus 3. Now I do need to put that in parentheses because that's all inside the log. And then that's going to equal the y minus 2. So I've rewritten it in log form. So I've gotten the y out of the exponent, but it's still not isolated. I still need to move that minus 2. So I'm going to add 2. Now be very careful. You are still not combining that 2 and that minus 3. That x minus 3 is inside the log. This plus 2 is not. So it has to stay separate. So I'm going to go ahead and rewrite that y as f of x, and it's the inverse. So that is going to be the natural log of x minus 3, close parentheses, and then plus 2. Another base e. So I know right away this should end up, the inverse should be a natural log if it starts as a base e exponent. So if this was a multiple choice question, these like C and D, when you see e is the base, eliminate anything that's not a natural log. It's got to be a natural log. Same thing going in reverse. If you start with a natural log and your inverse choices are all exponentials, get rid of anything that's not a base e. Natural log and e go hand in hand. All right, so replace f of x with y, switch x and y. All right, it's already isolated, done. So ready to rewrite as a log. So it's a base e, so natural log. Okay, my argument's just going to be x, and it's going to equal y plus 4. I've not isolated the y yet, so I still need to do this minus 4. Now that, again, just like over here, that plus 2 that we moved at the end was outside the log. This minus 4 is outside the log. So you can write this as the natural log of x and then minus 4. So that is technically correct. I would really like to put parentheses showing that that x is the only thing you're taking the log of. That minus 4 is outside the parentheses. You can write it with no parentheses. That's fine too. But you definitely cannot write it with the minus 4 inside parentheses. That's a different function. Y'all understand that? Okay. Last couple, and then you'll give it a shot on your own. We've got a log base 4. We're going to switch the x and y here. We've got to isolate the log expression, so that piece there. So I'm going to get rid of that 8 by adding it to the other side. Oh, hang on. I didn't draw. Look at that. Perfect example. I didn't put the parentheses, and those parentheses were definitely needed here. Oh, wait, highlighting. Okay, so that was log base 4 of y minus 8. So that y minus 8 needs to be in parentheses. That minus 8 does not move first like I was about to do because of those parentheses. So I'm ready to rewrite this in log form, or excuse me, exponential form. It's a base 4 to the power of x, and it's going to equal y minus 8. Now I move the 8. I do not combine the 4 and the 8. That 4 is to the power of x. That 8 is added on the outside. That's my inverse. So I write that as f inverse of x equals 4 to the power of x plus 8. All right, here is one where I'm going to rewrite, switch the X and Y. There is no parentheses here. So in this one, that constant does move first. Now I've isolated the log expression. I'm ready to rewrite this in exponential. So that's a base 8 to the power of x plus 12 equals y. And that's the inverse. So f inverse of x is 8 to the x plus 12. Now again, if you wanted to check any of those graphically, you could. You could plug in the original, plug in the inverse we came up with, and you should be able to physically see that they are a reflection of each other across that line y equals x. You'll give that exit ticket a try. I'm going to freeze the screen. If you're watching this as a video, pause the video and give it a try and then come back to chat. Does anybody think they've got one of them or both of them? I hope somebody is able to do one of these. Our test is over this in 2 days over logs. You've got to be able to convert back and forth between log and exponential form for solving the logs and here for finding inverses. Anybody think they did number 1 right? Well, tell us what you got. You don't have to go up to the board or anything. Just tell me what you think you got. Go ahead, Kira. Exactly. Log of x minus 6. Now the x can be in parentheses all by its lonesome, or you can have no parentheses at all. But you've got to make sure that minus 6 is not in the parentheses. Okay, I'll show the work here. I'll unfreeze the screen in just a sec. Does anybody want to share what they think they got for 2? You think you got that one too, Emma? Uh-huh. Good. Exactly right. So here, I'll unfreeze that screen. So you can see this is what Kira told us for 1, what Emma told us for 2. make sure that that -6 is not in the parentheses. You can just drop the parentheses completely if you'd like to, like it was here in the pink. Okay. I like to write it with parentheses to make it very clear the -6 is outside. Okay, here that +2 is outside as well. It's not in the exponent, it's outside. Okay, I'm not giving you a new assignment over just inverses, because again, we have done inverses with every unit. That's not new. The new part for this unit is the converting back and forth between log and exponential, which we've already been practicing with our other ALEKS practice. So no new assignment. Finish up your ALEKS. There's a practice 1 and a practice 2. There's 2 assignments in ALEKS from this unit. Okay, if you are not done with one or both of those, finish those up. Okay, if you have finished both of them, you should have your review and you can be starting or continuing working on your review for this unit. Remember, the review is due on Friday. The ALEKS practice 2 is due tomorrow before midnight. So if you haven't finished that, that's your priority. If you have, then you're starting or continuing the review. We've got, let's see. Look at period. Oh, the bell's about to ring. Okay. So you can come to tutorials if you'd like to have a place to sit and work, or if you have questions, or if you want to correct your Unit 10 test or retake your Unit 10 test. I'll be here for tutorials for the rest of the week. You can come any day. No, hang on one sec. It's not quite 9. All right, go for it.